this video, we're going to talk about system crashes. Gotcha! You should have seen the look on your face. But seriously, there are a ton of different reasons why applications crash. When we come across a program that terminates unexpectedly, we go through our usual cycle of gathering information about the crash, digging in until we find the root cause, and then applying the right fix. Say, for example, that a user asks for your help with a problem on their computer. When you ask for details, the user tells you that the internal billing application crashed while they were trying to generate an invoice for a customer. Now, this could be caused by lots of different things. So what you need to do is reduce the scope of the problem. And remember, you'll want to start with the actions that are easier and faster to check. As a first step, you try looking at the logs to see if there's any error that may point to what's happening. But you only find an error saying application terminated and no useful information. So you check if the user can reproduce the problem by doing the same action on a different computer. You ask the user to try this out, and it turns out, on a different machine, they can generate the invoice just fine. So that means that the problem just has to do with the installation or configuration on that specific computer. Great news! You've already reduced the scope to something machine-specific. Another thing that you might want to check is if this happens reliably. Do all invoice generations fail? Is it confined to one specific product or customer? For this example, let's say that when you ask the user to try generating other invoices, it works just fine, even for the same customer. Okay, you think maybe this problem was with the specific order for that specific customer on that specific computer. That's rather suspicious. But not so fast. The user tells you that after creating all the invoices for the day, they tried to generate a report, and the application crashed again. But then it worked the next time. You double-check with other users and find out the application isn't crashing when they use it. So what does this mean? The application seems to be crashing randomly, but only on that computer. To further reduce the scope, you'll want to know if it's just that application or the whole system. To check this out, you can try moving away the local configuration for the program and using the default configuration instead. Or maybe even reinstalling the application. You might also ask the user if they've seen crashes on any other application. For this example, let's say that reinstalling the application and running it with the default configuration still leads to random crashes. And when pressed to remember, the user tells you that their web browser also crashed last week when they were using the internal webmail. At this point, the information points to a problem in the overall system, either the hardware or the OS installation. If you have a spare computer available, it might make sense to give one to the user at this point, so that they can go back to work while you try to figure out the root cause of the problem. What can you do to further reduce the scope? By now, there's a high likelihood of the problem being hardware related. So one thing you could do is try taking the hard drive out of the computer and putting it into a different computer. This works best when you already have a spare case that you know works well, so that you can use it for tests like these. That way, you can quickly check if it's a problem with the data in the drive or the rest of the computer. Let's say that after putting the hard drive in the other computer, the applications run without unexpected crashes. This means that some hardware component is at fault. The next step is to find out which one. Given the random crashes, one thing to check would be the RAM. Memory chips deteriorate over time, and when they do, the computer might write data to some part of the memory and then get a totally different value when trying to read it back. To check the health of our RAM, we can use the memtest86 tool to look for errors. We run this tool on boot instead of the normal operating system, so that it can access all of the available memory and verify if the data written to memory is the same when it tries to read it back. If the RAM is fine, you can check if the computer is overheating by looking at the sensor data provided by the OS. And if that's not the case, check if there's a problem with external devices, like a graphics card or sound card. You can do this by disconnecting or replacing the devices present in the computer and checking if the crashes still occur. So what can you do if, when putting the hard drive in a separate computer, you still get the strange crashes? This means the problem is in the drive itself, or the OS installation. As with RAM, our hard drives age, and at some point, the data that the computer reads stops matching what was originally stored. Each OS ships its own battery of hard drive checking tools, and you should familiarize yourself with ones in the OS you're working with. You'll want to look at the output of the tools that check the disk for bad sectors. And you'll also want to use these smart tools, which can help detect errors and even try to anticipate problems before they affect the computer's performance. And what can you do if the hard drive turns out to be fine? You'd need to look into the possible OS issues. But before doing that, ask yourself, is it worth it? Looking into what's wrong with the installation can take a lot of valuable time. If the installation is easy to replicate, then just reinstalling the OS might be faster and simpler than looking into why it broke. Alright, so that's a glimpse of how you can try to diagnose a system that's unstable and behaving in weird ways. But often, you'll be dealing with a specific application that's misbehaving. In this case, it's almost certainly a bug in the application's code that's not taking into account a situation that, though unexpected, can sometimes occur. Up next, we'll check out what you can do when that happens. When an application crashes and we don't know why, we'll want to look for logs that might relate to the failure. To look at logs on Linux, we'll open the system log files in varlog, or the user log files in .xsessionerrors file. On macOS, we generally use the console app to look at logs, and the event viewer on Windows. So what kind of data should you look for in these logs? Most logs have a date and time for each line logged. Knowing when the application crashed, you can look for a log line around that time and try to find an error message related to the application that crashed. Sometimes the errors will be self-explanatory, like permission denied, no such file or directory, connection refused. Sometimes it will be a cryptic message, and you have no idea what it means. Whenever we have an error message, no matter how weird it seems, we can search for it online to try to figure out its meaning. If we're lucky, we might find the official documentation of what that error means and what we can do about it. But even if that's not available, we'll usually come across posts by others who've tackled a similar error. And this additional information can help us understand what's going on. If there are no errors, or the errors aren't useful, we can try to find out more info by enabling debug logging. Many applications generate a lot more output when debugging logging is enabled. We might need to enable it from a setting in the application's configuration file, or a command line parameter to pass when running the application manually. By enabling this extra logging information, we can get a better idea of what's actually causing the problem. And what do we need to do if there are no logs or error messages at all? In that case, we need to use tools that let us see what's going on inside the program. We called out a few already. On Linux, we use strace to see what system calls a program is doing. The equivalent tool is called dtruss on macOS. Process Monitor is a Windows tool that can also take a peek inside what's going on inside a process on Windows. By tracing which system calls a program is doing, we can see what files and directories it's trying to open, what network connections it's trying to make, and what information it's trying to read or write. This can give us a better idea of what caused the actual problem. We could find that the problem is caused by a resource not being present that the program expects to be present, like we saw with the missing directory example in the earlier module. Or we could find that the program tries to interact with the graphics interface and there isn't any because it's a service running on a server. Or the program tries to open a file, but the user running the software doesn't have the necessary permissions. If the application used to work fine and recently started crashing, it's useful to look into what changed in between. The first thing is to check if the issue is caused by a new version of the application itself. Maybe there's a bug in the new version that causes the crash, or maybe the way that we're using the application is no longer supported. But that's not the only possible change that could trigger crashes. It could also be that a library or service used by our application changed, and they no longer work well together. Or it could be that there was a configuration change in the overall environment, like if the user isn't in a specific group anymore, or if the files that the application used are in a different location. When trying to figure out what changed, logs can also be a useful source of information. In the system log, we can check which programs and libraries were recently updated. Checking for configuration changes might be harder, depending on how you manage that configuration. If the settings are managed through a configuration management system and the values are stored in a version control system, then you might be able to look at the history of changes and figure out which one triggered the failure. We called out a few times already how important it is to have a reproduction case for a problem that we're trying to solve. When we're trying to debug an application that crashes, finding a reproduction case can help us both understand what's causing the crash and figure out what we can do to fix it. So, it's valuable to spend some time figuring out the state that triggers the crash. This includes the overall system environment, the specific application configuration, the inputs to the application, the outputs generated by the application, the resources it uses, and the services it communicates with. When trying to create the reproduction case, it might be useful to start from a clean slate and slowly put the pieces in place until the crash triggers. This might include trying out the application with the default configuration instead of the local one, or on a freshly installed computer instead of the computer where it's crashing. And remember, we want to make the reproduction case as small as possible. This lets us better understand the problem and also quickly check if it's present or not when we attempt to fix it. And even if we end up unable to fix the issue, having a small and simple reproduction case is extremely helpful when reporting a bug to the program's developers. So to sum this up, to find the root cause of a crashing application, we'll want to look at all available logs, figure out what changed, trace the system or library calls the program makes, and create the smallest possible reproduction case. After doing all of this, we should have some idea of what the root cause of the issue is, and maybe even how to fix it. The strategy for fixing problems will depend on whether we can fix the code or not. One of the great things about working in IT is that we can tell the computer what to do and it will follow our orders. When dealing with unexpected behavior in the software written by other people, though, we might not always be so lucky. It could be that we're dealing with proprietary software and the source code isn't available at all. Or we might have access to the source code, but it's written in a language that we don't understand, and so we can't change it. No matter the reason, what can you do if you need to fix an application that crashes and you can't change the code? You'll need to figure out a way of working around the problem and avoiding the crash. The actual workaround will depend on what the issue is that you're trying to solve. Let's do a rundown of some of the available options. Say you figured out that the issue was caused by a specific data input that makes the application crash. The crashes only happen when the input isn't in the format the code expects. Some of your systems generate data in XML format, which used to work fine with the previous version of the software. But the new version now requires all data to be in a YAML format. In this case, you could write a script that pre-processes the data and make sure that it's in the format that the program expects. Similarly, if the problem is caused by an external service that the application uses and that's no longer compatible, we could write a service to act as a proxy and make sure that both sides see the requests and responses they expect. This type of compatibility layer is called a wrapper. A wrapper is a function or program that provides a compatibility layer between two functions or programs so they can work well together. Using wrappers is a pretty common technique when the expected output and input formats don't match. So if you're faced with some sort of compatibility problem, don't be afraid to write a wrapper to work around it. Another possibility you might need to look at is if the overall system environment isn't working well with the application. In this case, you might want to check what environment the application's developers recommend, and then modify your systems to match that. This could mean running the same version of the operating system, using the same version of the dynamic libraries, or interacting with the same backend services. Say the application was developed and tested on Windows 7. If you run into problems while trying to run it under Windows 10, you might want to use Windows 7 instead. Or, if the application was developed and tested for Ubuntu and you're having trouble running it under Fedora, you might want to try running it on Ubuntu instead. And what can you do if you can't make the environment match? This could happen, for example, if there's another application that requires a different version of the same library, or you can't change a certain configuration setting because it's required to access a different service. In this case, you might want to consider running the application inside a virtual machine, or maybe a container. These are two different things, but we won't go into details of how they're different here. All you need to know right now is they both let you run the affected application in its own environment without interfering with the rest of the system. This is what we need if we want the environment to be different than the one other applications are using on the same computer. Sometimes, we can't find a way to stop an application from crashing, but we can make sure that if it crashes, it starts back again. To do this, we could deploy a watchdog. This is a process that checks whether a program is running and, when it's not, starts the program again. To implement this, we need to write a script that stays running in the background and periodically checks if the other program is running. Whenever the check fails, the watchdog will trigger the program to restart. Doing this won't avoid the crash itself, but it will at least ensure that the service is available. This works well for services where availability matters more than running continuously. And no matter how you work around the issue, remember to always report the bug to the application developers. As we called out, if you have a good reproduction case for your issue, it makes it easier for the developers to figure out what's wrong and how to fix it. So when you report a bug, make sure you include as much information as possible. Share a good reproduction case, and answer the questions that we mentioned earlier on. What were you trying to do? What were the steps you followed? What did you expect to happen? What was the actual outcome? Up next, we'll see how to apply these skills to troubleshoot an application that's crashing. A colleague has alerted us that a web page on our web server isn't working. As we've done before, we need to figure out what this means exactly. We asked our colleague for more details, and they told us that the failing web page is at site.example.com/logs. Let's check out if this is failing for us as well. There it is. The server responded with a 500 error. This error usually means that something on the server side of the application crashed. But we have no idea what. We'll need to investigate to find out more information. Let's connect to the web server and try to figure out what's up. The first step is looking at logs. As we called out, on Linux systems, logs are located in var log. To do that, we'll use the date command to check the current date. Let's change into that directory and check out if there are any recent logs about our error. And then the ls-lt command, which sorts the files by the last modified date, connecting it to the head command to keep the top 10 lines. We just triggered the error, but there doesn't seem to be anything recent in the logs. Just in case, let's check out the last lines in syslog using tail. Nope, nothing interesting here. We need to figure out how we can get more information, but we don't even know which web serving software is being used on this computer. But we do know that the web server is running on port 80, the default web serving port. How can we find which software is listening on port 80? We can use the netstat command, which can give us a bunch of information about our network connections depending on the flags we pass. This command accesses a bunch of sockets that are restricted to root, the administrator user on Linux. So we'll need to call it with sudo, which lets us run commands as root. And then we'll pass a bunch of flags to netstat. We'll use -n to print numerical addresses instead of resolving host names. L to only check out the sockets that are listening for a connection. And P to print the process ID and name to which each socket belongs. And since we only care about port 80, we'll connect that output to a grep command, checking for :80. We got new information. We see that the process listening on port 80 is called Nginx, one of the popular web serving applications out there. We now want to check out the configuration for our site. Configuration files on Linux are stored in the etc directory, so let's look in etc Nginx. There's a bunch of files here, lots of different configuration options that you can set in the web server. We're looking for the configuration related to a specific site, so let's look in etc Nginx sites enabled. There are two files here, one for the default site and one for the site.example.com site. That's the one we want. Let's open it with the VI editor. There's not a lot here, but at the bottom, we see that it says UWSGI pass, and then the localhost address followed by a different port number. It seems that this website isn't being served directly from Nginx. Instead, the software is passing the control of the connections to UWSGI, which is a common solution used to connect a web server to programs that generate dynamic pages. So let's see if we can find the configuration for that one. We'll exit VI with the :Q and then see if there's anything interesting in etc UWSGI. Here we only see two directories, apps available and apps enabled. Let's see what's in apps enabled. Cool. We found the UWSGI configuration for our site. Let's check it out. Nice. This file has a lot more information. We see that the main directory for the application is srv site.example.com, that the applications run as the www data user and group, that it's running a Python 3 script called prod.py, that the log is stored in var log site.log, and a bunch of other things. All right, let's use this extra information and see if we can find out what's up. Let's exit with :Q once more, and then check out that log file. Weird. The log file has a size of 0. That doesn't seem right. Let's see if we can find out anything else by looking at the Python script that's executed by UWSGI, srv site.example.com prod.py. There's a few different web pages configured in this file. It uses Bottle, which is a Python module to generate dynamic web pages. At the bottom, we see the configuration for the logs page that's currently failing. Helpfully, a colleague left a comment saying that we can get debugging information by uncommenting the line that calls bottle.debug. That's exactly what we need. To uncomment this line, we need to have write access to the file though. And VI is open in read-only mode currently. Let's exit and open again with sudo to be able to modify it. Okay, we've made the change. Let's save it and reload UWSGI as the instructions say. We'll do this by running sudo service UWSGI reload. Okay, we've added debugging information. Hopefully, that will tell us why the page is failing. Let's reload the website and see what happens. Great news. This time, we see a traceback of the error, and we see that the issue is that the application is getting a permission denied error when trying to open var log site.log. Remember that we thought it was weird that the file was empty? It seems that it's somehow broken. Let's look at it again. This time, let's check if there are any other files that start with site. So there's a site.log file and a site.log.1 file. That's pretty common when using log rotate to rotate the logs and avoid them getting too big. But there's something else afoot here. See how one file belongs to the root user and the other belongs to the www data user? If you look at the permissions of the file, you might notice that they are set to allow the owner to write them and the owner and the group to read them, but the rest of the users can't access them. And we saw earlier that the application is running with the www data user. So, if site.log belongs to the root user, the application won't be able to either read or write to this log file. Ding, ding, ding. Seems like we found the root cause of our issue. Let's change the owner of the site.log file to fix the immediate problem. Let's try reloading our page now. Yes, it works. The log is empty now because the application had not been able to write to it. But if we keep reloading, we'll see how it populates with our entries. All right, we've fixed the immediate problem. Our web page is working once again, but we still need to take care of the long-term remediation. Why was the ownership of the file wrong? We suspect that there might be something wrong with the log rotate configuration, but we need to keep looking to find out what's up with that. In this video, we looked into how we can figure out what's up with an application that's failing. We checked out a bunch of different tools and ideas that can help us understand what's going on and get more information until we can find the root cause. I hope you're starting to see how these lessons provide valuable tools for diagnosing and solving issues that will for sure occur at your job.
Congratulations on finishing this lesson in the Google IT Automation with Python certificate. Access the full experience, including job search help, and get the official certificate by clicking the icon or the link in the description. Watch the next lesson in the course by clicking here, and subscribe to our channel for more lessons from upcoming Google Career Certificates.